tangent properties that could possibly happen. So we already know from a previous section that a tangent line is a line that intersects the circle at exactly one spot or exactly one point, which is called that point of tangency. Sorry, I didn't mean to get that part. But again, it is called a point of tangency. So if I tell you you have a tangent line, you automatically have that point of tangency, and vice versa. If I tell you you have a point of tangency, then the line must then be tangent to your circle. So now that we start to bring in more than one circle, we also get what's called a common tangent. And for us, a common tangent could be a line segment, or it possibly could be a ray. Sorry, that does not look like the word ray. There we go. Could be a line, a segment, or a ray that is tangent to two or more circles, is what gives us that common tangent. So when we look at different ways that we can start combining and bringing together our circles, we're going to start with just two circles. So depending on how your circles are arranged with each other, if your two circles intersect at one spot, then there is a tangent line at that one position. If my two circles, again, are side by side, I could have a tangent line across the top where it intersects again at one point each, or maybe even one down the bottom. Sorry, that doesn't quite, there we go. Okay, so for this situation, I end up with three common tangents between those two circles. Now, figure B, this time your two circles overlap each other, so I lose that tangent line in between there. Because if we did have that tangent where those two circles touch, well, problem is tangent lines intersect only one time. This situation, if I drew through the middle, would cross it twice. And that gives us actually a secant line, not a tangent line. So I lose the one in the middle. I do still have them on the outer edge though. Sorry, that's not straight at all. There we go, that's a little straighter. And I have one along the bottom edge here, very similar to the first picture, with 2 points of tangency on that line and two common tangents. Let's look at some of our other possible ways that we could combine our circles. Now I have one circle inside the other, and these two circles do have a common point, and that is all the way on the right where the two circles meet. So in this case, I only have one common tangent. Because one circle is inside the other, no matter where I draw a tangent line on that inside circle, it will always cross the big one twice. And no matter where I draw one on the outside circle, it will never reach the inside smaller circle. So it's not possible to have any more types of tangents when one circle is inside the others. It's just not physically possible. Sorry, bear with me, just trying to erase my extra marks here. All right, so looking at another kind of situation we might have, two completely separate circles from each other. They are not intersecting, so I do not have one line through their point of intersection. I still get the ones on the outer edges. But now for the other two, we have to kind of think outside of the box here. Because there is now space between my two circles, I also get diagonal lines here between my two circles. So I get these slanted two, they're a little more slanted than the others, for two more common tangents. So I really in turn get four common tangents when my two circles have some space. So now let's look at some of our tangent properties. So we have the property that says a line is tangent to a circle if the line is perpendicular to the radius. So again, my line, this line that's possibly tangent, is only tangent if it is perpendicular to the radius of that circle. And again, it goes the opposite way. If my radius is perpendicular to the line, then that line must be a tangent line. So it goes both directions. So with that, let's check out our example 2. Segment RS is a radius of the circle. So they're telling me R to S is a radius. Is segment ST tangent to this circle? Well, if it is supposed to be tangent, then the property says it should be perpendicular. So we need a way to prove that this is in fact perpendicular or not. So check out the picture they've given us here. It is a right triangle. And if this is a right triangle, then I could use Pythagorean theorem to verify that this is in fact a tangent line, and we are making that right angle. So let's focus only on that triangle for a second. We have R was the center of our circle, S was the possible point of tangency, T was on the outside. Point S had the right angle, and if I'm using Pythagorean theorem, across from that is my C side. The A and B, in all honesty, do not matter which is which. I let my shorter side be A and the longer one be B. So R to S, it says, is 5. So then my A side has a 5. S to T, it says, is 12. So I'm going to let my B be 12. What I need right now is my side RT, or my C side for Pythagorean theorem. So let's go back to our original picture. This 8 only goes to this outside portion of my circle. It is not all the way across. But one of the things that we've mentioned in the past, if I know the length of my radius, then I know how far it is to the outer edge. So if R to S is 5, any radius segment I draw in this circle would have to be a 5. So that means the other piece of my triangle that's inside the circle also has to be 5. So altogether, my side is 13. So there's my C side, a 5, a 12, and a 13 for the whole triangle. So again, if this is tangent, we'll have a right triangle. And if I have a right triangle, Pythagorean theorem should work. So when I take my C and square it, it should equal the A value squared plus the B value squared. So let's plug this in. C is 13, so 13 squared. A is 5, so 5 squared. B is 12, so 12 squared. So I have 169 on the left. 5 squared, 25, plus 12 squared, which is 144. And so they do come out to be equal. So this did come out to work. So therefore, segment ST is tangent. If those two sides did not work, this is not a right triangle, meaning it's not a tangent line because I don't have the 90 degrees. So let's look at one of our next properties. So now we have a property still dealing with our tangents that says tangent segments from a common external point, in external meaning on the outside, are going to be congruent. So with that, when I look at circle P, my point R is a point of tangency, point T is a point of tangency. Both of these segments intersect at the exact same point outside of this circle, which in turn means since they both intersect at point S, they have to be congruent to each other. That's what it means by if they intersect at that common exterior point. Now with that, let's even bring in an extra circle. If I start with just the circle on the right, so ignore the one on the left for a minute. If I look at the one on the right, I have I have a common external point. Look at your tangent segments. Both of these two tangent segments intersect at that point towards the top. So therefore, since they intersect at the same place, those pieces have to be equal. Now let's bring in that larger circle. Its two tangent segments intersect at the same place. So therefore, they are going to have to be equal. Well, my tangent segment there in the middle already has two dashes on it, which means that third one is also going to have the same number of dashes. All three of those have to be congruent to each other. If I added another circle, no matter the size of it, if this point of tangency intersects at the same place, it's going to have to be the exact same length as well, and it would have to be congruent. So no matter how many circles I add to this, no matter how big or how small they are, those lengths are going to have to be the same of those tangents if they intersect at the same place. So with that, let's look at example 3. Segment QR is tangent to the circle at point R. So point R, point of tangency, that's this entire tangent segment, which is 32. The next one says segment QS is tangent at point S. So point S, point of tangency, all the way out to Q. Guess what? They intersect at the same place. So therefore, these must be congruent to each other. So that means they will be equal when I try to solve this for X. They have to be equal in length. So my 32 has to equal 3X plus 5. And now I can solve this. So I'm going to subtract my 5 from both sides. So my 3X would equal 27. I can now divide by my 3. And my X is a 9. And that's all it wanted me to find was find X. So now let's say that circle has more than one point on the exterior and we have multiple tangent segments there, each of them going to different points. Well, when that happens, we get what's called a circumscribed polygon. We've already looked at inscribed polygons. That said, an inscribed polygon had all of the vertices on the circle's edge. Again, this was inscribed. When your polygon is inside, circumscribed reverses that, and now the circle is inside the polygon. So when that happens, when a polygon is circumscribed about a circle, all sides of that polygon are tangent to the circle. So with that one word, I automatically get my tangents. So if I look at example 4, example 4 says triangle ABC is circumscribed. So that is my important word there about the circle. Find the perimeter of this triangle. So I have 3 external points here. And each of the tangent segments that are going and connecting and intersecting at those common points will have to be congruent. So I've got point D as a point of tangency. So is point F, and so is point E. Those are my points of tangency. So that means D to A and F to A are going to have to be congruent. So if one of them is 12, so is the other. The same thing's going to happen at the top at point B. D to B and E to B are going to have to be congruent because they go to the same external point. So if one piece is 6, so is the other. And the same is true for the last one. F and E are both points of tangency, so therefore E to C and FC have to be congruent. So if one of them is an 8, so is the other. So now I can get the perimeter of this triangle. I need to add up all of those little sections. So I have 2 12s, 2 6s, and 2 8s. So all of that together gives me 52 for my perimeter. So add up all of our pieces. So now let's look at the next example. Example 5 says quadrilateral RSTU is circumscribed about circle J. So there's our important word again, circumscribed. This time, if the perimeter is 18, find the value of X. So it's the same situation. AS and DS would have to be congruent. So therefore DS must be 3. Same thing for D to R and C to R. If DR is 3, so is CR. And the same thing's going to happen at the top 2 corners. AT and BT are going to have to be congruent, and BU and CU are going to have to be congruent. So if CU is X, so is BU. If AT is X, so is BT. So now we've got all of our pieces. Let's see what we have here. Let's set up our equation. So it tells me the perimeter is 18. So in that figure, I had 4 3s. So 3 plus 3 plus 3 plus 3. Again, there were 4 of them along the bottom sections. Then I had 4 X's on top. So plus my 4 X's on top has to be 18. So combine like terms. All of these 3's make a 12. So 12 plus 4X has to be 18. Now let's solve this. So let's subtract that 12 to both sides. So my 4X has to equal 6. Divide both sides by that 4. And my X is 1.5. Or you could easily have 3 over 2, just depending on which way do you need to actually answer the question. Either of them are accepted. So again, you could have 1.5 or X could be 3 over 2. Either of these are correct. Last example, example 6. JKL, triangle JKL, sorry, is circumscribed about circle R. Find X and the perimeter. So similar situation. Let's match up our pieces first. So MK and NK are going to have to match. So NK is going to have to be 7. Same thing is true for M to J and O to J. They're both going to have to be 12 because they are going to be congruent. And then my last and final corner, OL and NL, are going to have to be congruent. So there's where I can solve for my X. So my X plus 3 has to equal 4X minus 9. So let's subtract that X to both sides. My 3 is equal to 3X minus 9. Add the 9 back. My 3X is a 12. When I divide out that 3, my X is a 4. So there's the first piece. Now I need to go back and plug this in. So 4 times 4 minus 9 gives me a 7. If I do that to X plus 3, 4 plus 3 gives me a 7. Now I can add up all of my pieces. I have 2 12s. I had 2 7s. And now I have 2 more 7s from the ones we just found. So all of that means my perimeter is another 52. So guys, I hope you enjoyed learning a little bit about your circles and about your tangent properties now to those circles. Please don't hesitate to reach out if you have any questions at all.